warning. Mr. Noisy is back. You may remember him from some of my previous videos. For this project, I am using an X9C103 digital potentiometer to control a sound generating device that I built. In fact, I built two separate modules. One is a popsicle stick creation where I made the X9C103 digital potentiometer more accessible to the user. I can plug jumper wires into female headers, which are hardwired to the digital potentiometer module. The other module I built is the classic Mr. Noisy. You may find other videos on my channel where I make use of the Mr. Noisy. The Mr. Noisy is basically a 555 timer circuit used to oscillate and create noise. On the Mr. Noisy, the sound changes as the resistance from the digital potentiometer is swept between 0 and 10 kiloohms. This causes the oscillator to increase and decrease in pitch. Well, it changes the oscillation in the Mr. Noisy. The digital potentiometer is controlled by a Raspberry Pi 4, which drives the control pins directly. I'm not using the non-volatile memory feature of the X9C103, so the CS pin is not used. All of the required control signals are generated by the Pi as output pins. To interact with the system, I implemented two Raspberry Pi input pins, each assigned a specific behavior. One input steps the potentiometer value up incrementally, while the other steps it down incrementally. This allows the resistance of the digital potentiometer to vary, which in turn changes the pitch of the Mr. Noisy. All of the control logic for this setup is written in Python, making it easy to modify and experiment with different behaviors. For viewers who are unfamiliar, here is a quick explanation of the X9C103 digital potentiometer. The X9C103 is a digitally controlled potentiometer. Inside the device is a chain of resistors and a movable wiper that selects different resistance values. The wiper is controlled using 3 digital control pins. The resistance is adjusted by moving the wiper up or down through a series of fixed steps. The X9C103 has 99 internal steps, allowing the resistance to be changed in small, repeatable increments. The current wiper position can be saved in the device's memory and automatically restored when power is turned back on. The X9C103 can be used either like a standard 3-terminal potentiometer or as a 2-terminal variable resistor, making it useful for things like signal control, tuning, and adjusting circuit behavior. Here's a simple explanation of just the UD, INC, and VW pins on the X9C103 digital potentiometer based on the data sheet. Pin functions. UD, up-down pin. This input sets the direction you want the wiper to move. When you toggle the INC pin, UD tells the chip whether to step the wiper up toward higher resistance or down toward lower resistance. Inc. Increment pin. The Inc pin controls changes. Every time you pull this pin from high to low, a negative edge, the chip moves the wiper one step in the direction set by the UD pin. VW wiper pin. This is the potentiometer's output terminal. It's the moving contact of the internal resistor network. Its voltage or resistance changes as you step the wiper position using the control pins. Brief note, the CS pin can store the current resistance setting. I didn't make use of it in my project. Alright, please allow me to explain the code line by line. Import rpi.gpio as GPIO. Imports the Raspberry Pi GPIO library. This lets Python control the Pi's physical pins, read buttons, toggle outputs, etc. We rename it to GPIO for shorter, cleaner code. Import time. This imports Python's time library. It's used for delays, sleep, so pulses and button timing work correctly. This section is the GPIO setup section, and the code is written as gpio.setMode in parenthesis gpio.board. This tells the GPIO library to use physical pin numbers on the Pi header. Example, pin 11 means the actual pin labeled 11 on the board. This avoids confusion if you're wiring by pin location instead of BCM numbers. Next line of code, gpio.setWarnings false. This turns off warning messages. It prevents annoying alerts if a pin was previously used or not cleaned up properly. Here are the X9C103 pin definitions, and the code reads pin _INC equals 11, pin UD equals 13, pin CS equals 15. These variables store which physical pins are connected to the X9C103 digital potentiometer. Inc. Step pulse input. UD is the direction up or down. CS is chip select, and this controls memory storage. The comments show the BCM equivalent just for reference. Next, we configure the X9C103 pins as outputs. gpio.setup pin inc gpio.out. Next, pin UD is also set as a gpio.out. Pin CS likewise. This sets all three X9C103 control pins as outputs. The Pi will actively drive these pins high or low. The next line of code, gpio.output pin CS-GPIO.high. This sets CS high. On the X9C103, CS low writes to non-volatile memory. Keeping it high means no EEPROM writes, faster operation, and no wear on the chip's memory. The next section of code are the button pin definitions. BTN up equals 29, BTN down equals 31. These pins are connected to physical push buttons. One increases resistance, one decreases resistance. The next line of code is GPIO.setup button up GPIO.in, and a pull-up resistor is used. So to add emphasis, these pins connected to push buttons, which are connected to the pi as input pins, they have pull-up resistors. So they are normally high and activated when they receive a low signal. So these push buttons are both set up as inputs, and they have enabled on them internal pull-up resistors. So when the button is released in a resting state, it's receiving a high signal. When the button is pressed, it's receiving a low signal. This avoids needing external resistors. The next section of the code is the X9C103 control variables. Step_delay equals 0.001. This is a delay in seconds between ink pulses. This controls how fast the wiper moves. A smaller number equals faster stepping. Next line of code, current_position equals 50. Software only variable that tracks the wiper position. Valid range 0 to 99. 100 steps total. Starts at 50 as a middle-ish guess. Important, this does not read the chip, it's just your program's best estimate. My program's best estimate, excuse me. Step function. Def step direction steps equals 1. Defines a function to move the potentiometer. Direction, up or down. Steps, how many increments to move. Next line of code, global current_position allows the function to modify the global current position variable. Next line of code, GPIO.output pin UD GPIO.high if direction equals up, else GPIO.low. This sets the UD pin high equals increment increased resistance, or it sets the UD pin low, which equals decrement decreased resistance. Here is the stepping loop. 4 in range steps. This repeats once per step requested. Next line of code, if direction equals up and current position is less than 99, and this checks, are we moving up? Are we not already at the maximum position? Next line of code, GPIO.output pin inc GPIO.high time.sleep step delay. GPIO.output pin inc GPIO.low. These 3 lines of code generates 1 ink pulse, high, then wait, then low. This is what physically moves the wiper 1 step. Next line, current underscore position plus equals 1. This updates the software's position tracker. Next line, elif direction equals down, and current position is greater than 0. This is the same logic, but for moving downward. Prevents going to 0. Next lines of code, GPIO.output, pinInc GPIO.high, time.sleep, step underscore delay, GPIO.output, pinInc GPIO.low, current position minus equals 1. 1 pulse, 1 step down, then it updates the position. Next line of code, time.sleep, step delay. This is a small pause between steps. It helps keep timing clean and reliable. Now, here is the main program. Print X9C103 up-down controller board pins. Print starting position, current position. These are just status messages, so you know the program is running. Here is the main loop. Try, while true. This creates an infinite loop that runs until you press Ctrl and C. Next line, if not GPIO.input, button up. This line reads the up button. Not is used because button press equals low. Low evaluates as false. Next line, step up 1, time.sleep 0.05. This moves the potentiometer up by 1 step. This is a small delay that controls how fast repeated presses happen. Next, if not, GPIO.input, button down. Same logic for the down button. Step down 1. Time.sleep 0.05. Moves 1 step down. Time.sleep 0.005. Tiny delay to prevent CPU overuse and button bounce issues. The last part of the code is a clean exit. It reads except keyboard interrupt, and this triggers when you press Ctrl and C, and then it prints print exiting cleanly on a new line, and it has a friendly shutdown message which says finally GPIO.cleanup. This resets all GPIO pins to a safe state. It's very important so the Pi doesn't leave pins stuck high or low.